if you recollect, we have looked at the definition of random processes. We said that there are two ways of looking at a random process. One is to look upon it as a collection of waveforms which may occur randomly, right. Any particular waveform is picked up with a certain probability depending on the probability distribution of the underlying probability space, right. There is a mapping from omega to the set of functions which are functions of time. The other way is to think of it as a sequence, indexed sequence of random variables, where there is some kind of an index which brings out the functional dependence eventually. It could be a functional dependence on t, the index could be t, the index could be some spatial variable or any other kind of variable, right. So, you have a sequence one after another of random variables occurring with certain probability distributions, and that constitutes a random process. The later approach is convenient from the point of view of characterization of the random process in terms of probability distribution functions. Only thing is, the complete characterization is a very elaborate affair, and we discussed that it is very difficult for a complete characterization of an arbitrary random process, because you would then need to characterize the process at every time instant individually, at every pair of time instants jointly, and so on and so forth, for every triplet of points, every quadruplet of points that you can select, and therefore one requires an infinity number of probability distribution functions, marginal density functions as well as joint density functions of various orders to completely characterize the process. To simplify that process, to simplify the characterization, we made some assumptions about the process. We can make some assumptions, of course they must be valid if you are going to use this, but typically many of these assumptions are valid. One assumption that we made is the stationarity assumption, right. We define a strict sense stationary process as one whose probability distribution functions, or whose characterization, whose statistical characterization is independent of time origin, right, time shifts. So, these are the things that we covered last time. We also looked at the definition of certain moments of a random process, namely the mean value function and the autocorrelation function. So, we will start from that point onwards. So, to recap, the autocorrelation function is a second order characterization. Why do you say it is a second order characterization? Because we require a joint density function of the two random variables xt1 and xt2. So, let us call it Rx t1 t2, and repeating this point. So, you take the random variable values, random process values at time instance t1, let it be denoted by the value x1. Of course, this could occur anywhere from, this value could be anywhere, lie between anywhere between minus infinity plus infinity. Similarly for x2, multiply these two, multiply to the joint density function of these two random variables, right. So, this is one notation by which you can denote the joint density function of the random variables obtained by sampling the random process xt at the time instance t1 and t2, right. So, this is a notation. This t1 and t2, this does not mean that in general there will be a time dependence. Yes, there will be time dependence if the process is not stationary. If the process is stationary, the time dependence will only be in terms of t1 minus t2 rather than t1 and t2 separately, right. But yes, in general, since as much as this joint density function depends on the time instance chosen t1 and t2, therefore the autocorrelation function will depend on where you have sampled the random process, right. So, this is the general definition for strictly stationary processes. For stationary processes, this will be a function only of, or you could say this, you could write as Rx t2 minus t1, which could be written as Rx tau, where tau is defined to be the variable t2 minus t1. this is I think where we stopped last time. So now let's look at a few things. Let's look at the value of Rx tau for tau equal to 0. What does it mean that we are looking at? What is this equal to? You can think of this operation in terms of expectation operations as equal to expected value of xt1 into xt2, right? This integral is nothing but the expected value or the average value of the product of the two random variables obtained by sampling the process at time instants t1 and t2, right? So what is Rx0 in that case? If you choose t1 equal to t2, that will give you tau equal to 0, right? So you could say that this is equal to expected value of x square t for any arbitrary time instant t, right? So the value of the autocorrelation function for a stationary process at tau equal to 0 is going to be equal to the mean square value of the process, right? And it's a constant. Suppose the process was not stationary, then would this be a constant? No, right? In fact, we will not write Rx0 in that case. We will write Rx tt or t1 t1, right? And in general it will depend on the value of t. So this equivalently for a non-stationary process, the corresponding relation would be Rx tt, that is the chosen t1 equal to t2 equal to t, and this will be equal to expected value of x square t, that is correct, but this is going to be a function of time. It is not going to be a constant. In this case it is not going to be a function of time, it is going to be constant, right? Is it clear? So for a time for a non-stationary process, this is a relation. For a stationary process, this is the relation. Now it is clear from the definition of the autocorrelation function, at least for real valued processes, that if I interchange t1 and t2, if I interchange write xt2 first and xt1 later, it won't make any difference. You are just multiplying the same two numbers, right? The average value will be the same, right? What does it mean? That Rx tau will be equal to Rx minus tau, right? So this is an important property of the autocorrelation function for real valued processes, right?
Sir,
yes, please.
Rx0 you said that is for a stationary process. What is the difference between Rx t comma t and Rx0 sections?
They are same for stationary processes. This will become this for stationary process. For stationary processes, this will be equal to t minus, the argument can be replaced with t minus t. But in general, when it is not a stationary process, this is a relation you have to work with. If it is a stationary process, you can work with this relation.
And the stationary process is independent of time.
That's right, because the value of this autocorrelation function, as we discussed, will depend only on the separation of the two time instants rather than on the actual value of the time instants, because it is independent of the density function is independent of time origin, right?
So for Rx0 shouldn't we use Ex square of tau?
No. Please understand. It is what is Rx t1 t2? It is the effective value of xt1 into xt2. So all you are doing is choosing t1 and t2 will be the same time instants, right? The tau is 0 here, so there is nothing on this side. Choosing any time instant and looking at the mean square value, that is Rx0. Rx tau is a function of tau. When tau equal to 0, it becomes equal to the mean square value of the function. That is the point that you are trying to mention here. Is it clear? Look at the basic definition and things will become very clear. Okay. So this is true for real valued processes. So sometimes I will simply use the word process when I want to say random process. Okay. In general, you could also intuitively see that the magnitude of Rx tau, and of course you can prove it more formally, I'd like you to do that yourself. the magnitude of Rx tau cannot be more than the value at tau equal to 0, isn't it? Again, for the same reason, we can expect maximum correlation to occur when the two random variables are the same, right? The moment you sample them at different time instance, they are different random variables. They can have correlation, right? But obviously that will be less than the correlation that you will have of a random variable with itself. That will be perfectly correlated, right? So of course one can prove it mathematically, which I like you to do yourself. It's very easy to do. It's easy to check that the magnitude of the autocorrelation function for a lag tau, the variable tau is also sometimes called the lag variable, because lag between the two time instants t1 and t2, or the time difference t1 and t2 is always less than or equal to the value of the autocorrelation function at tau equal to 0. Please understand that Rx tau is not a random quantity, in case there is any kind of confusion in your mind. Rx tau is a highly deterministic function, right? It's a deterministic function because you are basically looking at this integral, right? It's a function of, so it's not a, unlike xt, which is a random process, Rx tau or Rx tt or Rx t1 t2, these are deterministic functions which are properties which describe the second order properties of the random process xt, right? It tells you the behavior of the random variables with respect to each other on an average by looking at the average value of their product, by sampling the random process at different time instance and multiplying these random variables and looking at the average value of this product. It's some kind of a characterization of the process, second order characterization of the process. It's a value, it's a fixed value for a given process, even though the random process xt is random in nature. It's the values that you will see are random in nature. There is nothing random about Rx t1 t2 or Rx tt or Rx 0 or Rx tau, right? The autocorrelation function is a deterministic function. So these are some of the properties of a stationary process. Incidentally, just I will mention it passingly here, and we will need it if need arises. If the process xt is a complex valued process, for example, if you are working with a narrowband process and you are looking at its complex envelope, then it will be a complex valued process, right? In that case, the definitions are slightly modified. The autocorrelation function is defined as xt1 into x conjugate t2, right? You do a conjugation operation, but we will use that when the need arises. Okay. Suppose, as I said, a strict sense stationary process would greatly simplify our characterization of the process, right? We discussed that earlier. In many instances in real life, when you are working with random signals or random processes, we don't really need to worry about distributions beyond second order, right? Typically, we are interested in characterizing the process in terms of individual values that you might see at various time instants, or in terms of joint behavior of a pair of values, right? Typically, you very rarely need to work with situations where you need to look at more than two values at a time, right? Which essentially means that we don't need to worry about characterization beyond second order characterization in many applications in practice, right? So if that be the case, whether the process exhibits stationarity in the strict sense or not is not the key issue. All that we really then want is that the process be second order stationary, right? And second order stationary means that the first order density function px t1x should be independent of t, and the second order joint density function px t1 x t2 should be independent of, should only depend on t1 minus t2, right? So if the process satisfies this time origin invariance only with respect to these two distribution functions, we say the process is second order stationary rather than strict sense stationary, right? In reality, we don't even worry about second order stationarity as engineers. It is sufficient for us if the first two movements of the process exhibit these properties, right? So if that happens, we are working with a process which is said to be stationary in the widest sense or wide sense. So, we define a notion of wide sense stationarity, which is a special case of strict sense stationarity would imply, of course, this. So, wide sense stationarity is defined as follows. If the mean value function, the variance function, which of course is redundant, because if the autocorrelation, and the third thing is autocorrelation, because autocorrelation would lead to variance as a special case, or if these two are independent of time, and if the autocorrelation function is a function only of T2 minus T1, T sub T2 minus T sub 1, namely is a function only of the difference variable tau, then the process xt is said to be wide sense stationary. This is a usual notation, WSS. Okay. So, what are we saying? We are not asking even the density functions to be invariant, even the first and second order density functions. We are only saying that the mean value function, remember what is a mean value function? How will the mean value function be defined? Mu xt would be simply equal to expected value of xt, right? That is the definition of mean. You are looking at the random variable at time t, looking at its average value. What is this going to be equal to? X px x, it will also depend on t in general dx, right. So, if it is a first order stationary process, pxt would not depend on t, right, and therefore, it is obvious that mu xt would be a constant, right. But our definition of a wide sense stationary process does not even require this to be independent of t. All we are saying is, if this is independent of t, that is good enough for us, right. We are looking only at the first order movement associated with this density function. Remember that, right. That is one. What is this variance? Variance is sigma x square t. It will be expected value of xt minus x bar t whole square, right, and how again this will depend only on the density function pxt, right. So, this will be equal to x minus x bar that will be the definition of the variance, isn't it? That is expected value of x minus x bar whole square. That means integral of x minus x bar and the density function associated with x, right. Again this is independent of t, therefore, this should be independent of t. But again in WSS we are not saying that this should be independent of t, all we are saying is that this should be independent of t, right. The second order movement should be independent of t. And finally, what we are saying is that our autocorrelation function Rx T1 T2 as defined earlier should be a function only of tau, right. Of course, the variance function is related to this function. If this will display this property, actually this will be automatically implied. This is something that you can check, right. So, if these three conditions are satisfied, actually two conditions, namely the mean value function is independent of time and the autocorrelation function is dependent only on the time difference between the two time instants t1 and t2, we said that the process is stationary, wide sense stationary, and many times we are quite happy if the process is wide sense stationary, because many times we do not even need to worry about the distribution functions, right. you only need to worry about the first and second order movement functions, namely the mean value function and the autocorrelation function. So, mean value function is the first order movement function, because the power of x that you are raising it to is 1, right. When you are taking the movement, it is a first order movement. The autocorrelation function is the various function of second order movement functions, and many times it is sufficient to work with the first two movements, right. They contain most of the physical information that we are generally interested in looking at the processes, right. So, we have therefore introduced the concept of a strict sense stationary process. A process which is stationary up to second order or third order would be a special case of that, but a wide sense stationary process is something which is altogether much more tolerant of non-stationarities. The process may be non-stationary, but it may be still stationary in the wide sense, right. So, what you have to appreciate is that if a process is strict sense stationary, this stands for strict sense stationary, it would obviously imply that it is wide sense stationary, isn't it? That obvious, should be obvious, I think. This would imply WSS property. The reverse will happen only in very, very special cases. WSS would not in general imply strict sense stationarity, right, because this is independence only in terms of movements, that also of the first two orders, right, and therefore we cannot say that all the density functions, all the complete statistical characterization would be independent of time origin, right. But in very, very special cases this could imply this, for example, for a class of processes which we call Gaussian processes, right, but that is very, very special. To give an example of a process which could be which is not strict sense stationary and yet it is wide sense stationary, right. I will just give you one simple example. I will leave the details for you to work out yourself, or maybe you can do that quickly here itself. Suppose I generate a random process in the following way. There are many ways of generating a random process, right. Let me define a random process which essentially becomes random by virtue of its dependence on it's a cosinusoidal function of time, right. It's a cosinusoidal function of time, but there are three parameters in this cosine function: the amplitude A, the frequency omega 0, and the phase theta, right. Let me make one of them, let us say the phase, a random variable. Let us say the value of theta is something that occurs randomly from one function to another function. If you look upon this as an ensemble of functions, right, every function in this collection would be a cosine function, but with a different phase, and the value of phase is governed by some distribution, right. So, in as much as you have a collection of functions, it is a random process. Is it clear? And that every function occurs with a certain probability, right. So, it becomes random if any one or more of its parameters are random variables. So, here this becomes random because we are assuming that theta is a random variable, let us say with uniform distribution. Let us say if I say it is uniformly distributed between 0 and 2 pi, then what will be the density function of theta? It will be equal to 1 by 2 pi over 0 and 2 pi and 0 elsewhere. Okay. This will imply that this is the density function of the random variable theta. You are with me? Okay. Let us look at the mean value of this. Let us look at the mean value function. We want to see whether this function is a function of time or not, right. Mind you, we are not looking at the density function of xt here. right now, but sometimes we can work around that. Even without computing the density function of xt, we can compute. See, this is the important point. We can compute this quantity even without knowing the density function of x of t, right? Because we know how to compute the expected value of any function of a random variable. So you can think of this function as a function of the random variable theta and compute its average value on that basis. So what will that be? It will be a cosine omega 0 t plus theta. You multiply with the density function of theta, right? Think of this as a function of theta, this entire thing at any given time, right? Multiply it with the density function of theta, which is 1 by 2 pi over 0 to 2 pi d theta. Is that okay? You have a function of theta, you multiplying with the density function of theta, integrating over the range of theta, over the domain of theta, right? That's one way of computing the expected. This here I am using the fact. Let me recollect for you. We discussed expected value of any function of x requires you to simply do this operation, isn't it? I am using this relation here. X here is our theta, variable theta. F of x is this function, right? You are multiplying with the density function of x, the density function of theta, and integrating over theta. Now look upon what will be the value of this integral? 0, right? So it is independent of time, right? So the value of this is equal to 0. Let's look at the autocorrelation function. Let's look at xt1 into xt2, or let's say more conveniently, let's write it as xt into xt plus tau, right? I have chosen t1 to be some arbitrary time instant t, and then t2 I have chosen as t plus tau, so that the difference between them is equal to tau, right? So this will be equal to 0 to 2 pi. Again, now the function is different, that's how. The function is now this product function, everything else will be the same. So it will become a square cosine omega 0 t plus theta into cosine omega 0 t plus tau plus theta. Multiply this with the joint density with the density function of theta, right, and integrate over theta, right, and a simple evaluation of this integral will show you that this is equal to a square by 2 into cosine omega 0 tau.
Should that be 1 by 2 pi whole square because we have a joint?
No. We are not looking at a joint density function. I am just looking upon this product as a function of theta. Again, I am using the same definition here, because I am not going through the path of first finding the joint density function of xt1 and xt2. That could be one way, but that is very complicated in this case. It is not necessary. It is in this case much easier to look upon this simply as a function of the random variable theta, this product function, right? Multiply with the density function of theta and integrate over theta. Okay, so you can see that after this integration, it is not going to depend on t. It depends only on tau.
Sir,
Right?
does theta changes with time also, or is just depending on its angle? Theta is fixed for a given time.
Please repeat your question.
Sir, this theta that you are taking, does it also depend on time?
No, theta is not dependent on time. Theta is a parameter of this function, right? Depending on the value of theta, you get a different time function, isn't it? These different time functions are all cosine waves of the same frequency and same amplitude, but starting with a different phase, right? So therefore basically this collection that you are looking at is a collection like this. right, and so on and so forth. It is an infinite collection. You can define a waveform for every different value of theta, right. So, either picking up this waveform or picking up this waveform or picking up this waveform, right. And when you are talking about the mean value function, you are saying, okay, if I pick up some time instant t, what is the average value that I am likely to see here across the ensemble? The answer is 0. If I pick up two time instants t1 and t2, which are separated by a time instant separated by some interval tau, what is the average cross correlation that I am going to see between these two random variables? Answer is cosine omega 0 tau, right. It does not depend on the choice of t1 and t2. This is what we have demonstrated, right. Is that clear? So, here is an example of a process which is obviously not strict sense stationary. Is it obvious that it is not strict sense stationary? Okay, it is not obvious. Actually, I am assuming that it is obvious. You think about it. It is not obvious, but it is possible to argue very easily. Okay, to see that, let us look at, let us say, one time instant like this. Now, I think it requires a little bit of thinking, and I think I will like to leave it here for the time being, because we are going to digress quite a bit. But it is possible to argue that its density function is not constant with time, right. Even the first order density function is not constant with respect to time. Actually, it is one of the problems in the book. Please look at the problem very carefully, and we will arrive at this argument. But even though the density function itself is a function of time, the first two moments, namely the mean value function, expected value of x of t, and the autocorrelation function, satisfy the required properties of a wide sense stationary process. So, it is not a strict sense stationary process, and yet it is a wide sense stationary process. Okay. So, is that okay? So, only you need to verify that it is not a strict sense stationary process. So, please do that as an exercise. Okay. Now, let us take stock of what we have discussed so far. We said that if you are working with a random waveform or a random process, we can characterize it for all practical purposes as electrical engineers. Most of the time, it is sufficient for us to characterize it with two kinds of functions. The mean value function, that gives us an idea of what is the average behavior of the time functions. What is the average behavior of the various time functions which constitute the process, right. That is one property. The second is the autocorrelation function, which tells us if I look at two random variables which are removed from each other by an interval of tau seconds, what will be the average value of the cross correlation of these two random variables, right. So, rather than trying to specify the density function and the joint density function, which has much more information, many a times as engineers we are sufficiently happy with these two informations, namely the mean value function property and the autocorrelation function property, right. In some cases we need to go into more detail, but many a times this is good enough, right. So, for our purposes, the function mu xt, which is going to be a constant function for a wide sense stationary process, and the function rx t1 t2, which is going to be a function only of tau for wide sense stationary processes, is good enough for us. You do not even worry about density functions in many cases, right. Now, as electrical engineers, we are used to describing things in the time domain as well as in the frequency domain, right. When we talk about a time domain function, we immediately ask ourselves, okay, what is its spectral domain description, what is its spectrum like, isn't it? You have worked out elaborate theory for doing that, namely the Fourier transform theory. You will have similar interests here. You have, after all, whether the signal is a deterministic signal or whether it is a random signal, it will have some properties both in the time domain as well as in the frequency domain, right. So, we like to also see whether it is possible to characterize a random process in the frequency domain. Now, let us see, let me just discuss a few basic concepts or conceptual difficulties associated with this, and then just give you the important result in this connection. Let us look at the difficulty here. Let us say we are defining a random process as a collection of waveforms, right? That is one way of looking at it. Now, when you take a Fourier transform, what is a Fourier transform? Fourier transform is, let us say you have a function x of t and you multiply it with e to the power minus j2 pi f t and take the integral from minus infinity to infinity, that gives you the Fourier transform. That is the usual known thing that you work with. What are the assumptions in this? The assumptions are that x of t is a energy signal, right? It is it's absolutely integrable, right? You remember the Dirichlet conditions associated with the definition of existence of a Fourier transform, associated with the existence of Fourier transform. So one of the requirements is that xt should be absolutely integrable. That means it should be an energy signal rather than a power signal. Now, when you are working with random processes, you do not know whether you will be working with energy signals or power signals. That is one issue, one difficulty that you need to work with, right? Your functions may be power signals, your functions may be energy signals. But that is a problem that we have also dealt with in the context of deterministic signals, and we typically get around that by introducing impulse functions in the frequency domain, right, if you recollect. But that is one problem. The second problem is more difficult, more conceptually more difficult to handle. X of t was a very well defined waveform, very well defined mathematical function of time, right, whose Fourier transform you are taking, for example, e to the power minus alpha t or cosine omega 0 t, right. But the collection, when you talk about x of t being a random process, you do not know what waveform you are working with actually. It is one of infinite number of waveforms, and every one of them, even if the Fourier transform were to exist for that waveform, would have a different Fourier transform, and therefore would have a different kind of spectrum. So what should we talk about? Does it make sense to talk about a Fourier transform or the spectrum in the normal sense? Answer is no, it does not make sense, right. However, what does make sense is, on an average, what is the energy distribution as a function of frequency, or what is the power distribution as a function of frequency, depending on whether we are working with energy signals or power signals, right. So the important frequency domain concept for random processes is not the usual spectrum, which is just a Fourier transform of a function, but a average kind of function which is known by the name of power spectral density function. First, let us define this power spectral density function conceptually, right. Okay. Let us say we have a random process x of t. Okay. So what we will do is to convert this into an energy signal. I will first truncate this process. So let us draw some random waveform. Let us look at this waveform between, let us say, minus t to plus t, right. This portion of the waveform, I am talking of one sample function of the process. Here I am looking at one sample function of the process. As you know, a random process is an infinite collection of such sample functions, right. It is some arbitrarily selected sample function from that collection. Okay. So you pick up one and truncate it between minus t to plus t, denote the resulting process x sub tt. So x sub tt has been generated from xt by looking at it in the interval between minus t to plus t and making it 0 outside this interval. This artificial construction ensures that I have converted even a power signal into an energy signal, right. Is that clear? Because now it will have finite energy, and therefore the Fourier transform of this would be defined. But then, since again this is a random quantity, I do not want to take the Fourier transform of this, right. What I am interested in, what is the, first of all, I will square this function because I am only interested in the power or energy. I am not interested in the individual functions values by themselves, right. squaring is a measure of the energy at various time instants, right. This is of course not literally, but in some approximate sense. So, what I will do is no, I think I am going on a wrong tangent. So, now let me define the Fourier transform of x t t. Although I am using the capital letter, please remember I have picked up one sample function, right. I picked up one sample function, and that sample function is now an energy signal, and I am taking its Fourier transform, right. This Fourier transform would exist now, whatever the function may be, whichever I have picked up, it does not matter, because I have converted this into an energy signal, the Fourier transform will exist. Alright, so I take the Fourier transform. This will now become a function of frequency, right. Take the magnitude square of that, right. Now, this will be the magnitude square or the energies as a function of frequency of one sample function that I picked. If I want to look at the average value, average properties, what should I do? Take the average value of this, right. And if I want to convert this energy function, this is an energy function, isn't it, into a power function, what should I do? Divide it by 2t, because my function duration is 2t, and if I want to look at the original function, take the limit as t tends to infinity. So, this motivates my definition of the power spectral density function of a random process x of t. I have denoted by S sub x f as limit as t tends to infinity of 1 by 2t expected value of the magnitude square of the Fourier transform of x t t. Look at this carefully. I have gone through the argument leading to this, but if you have any doubt, please ask your questions. That is a formal definition of the power spectral density function, and it is a measure of the average distribution of power for the given random process x t in the frequency domain, right. How is the power distributed amongst different frequency components in the frequency domain? Are you with me? Do you have any questions? So, that's, you can take that as a definition. Now, without going through the details of a result, I will just like to give you a result which you should know of, which is a very important result in the characterization of random processes. It relates the density function, the power spectral density function. When I talk about density function of a process, you must ask whether you are talking probability density function, whether you are talking about power spectral density function. Power spectral density function is a I mean, it's a what should I say? It's a second order characterization once again. Do you agree with that? Because you are taking the random process and I guess you are not squaring it up in the time domain, you are squaring it up in the frequency domain, but you are anyway squaring it up, right, and you are taking the average value of that squared and a function of frequency, right. So, it is a second order movement, just like the autocorrelation function was a second order movement, right. So, if you look at it this way, it must be natural to expect that these two second order movements must be somehow related, isn't it? We are saying that the autocorrelation function is a second order movement description of the random process x t, and now we are saying similarly that this function that we just defined, the power spectral density function, is also a second order movement characterization in some sense. Only thing is, this is a frequency domain characterization, that was a time domain characterization. Therefore, it sounds logical that these two second order movement descriptions should be related to each other. right, and that is the important result I am talking about. There is a very simple way to, not exactly very simple, but it is possible to show that these two things, the second order movement description in time domain, which is autocorrelation function, and the second order movement domain in the frequency domain, which is the power spectral density function, are essentially Fourier transform pairs, right. So, which is a result very similar to what we are used to doing for deterministic signals. Only thing is, there we take the Fourier transform of the signal directly. Here we are taking the Fourier transform of the autocorrelation function, right. This result is known by the name of Wiener-Khinchin theorem, which essentially states that the power spectral density function of a process xt and the autocorrelation function of a process xt are Fourier transform pairs. One determines the other. So, PST, let me put here like that. An autocorrelation function of Fourier transform pairs. Okay. And therefore, in as much as the mean value function and the autocorrelation function are complete second order characterization of a random process, similarly the mean value function and the power spectral density function are complete second order characterizations of the random process. Okay. Let me now finally define one more concept, and then so next time we'll essentially concentrate on the concepts that we are specifically going to need in our treatment of the communication systems. The final concept is the concept of ergodicity. I will just mention it here. We will not really go into a very detailed discussion of this concept, but we need to know it, right, at times. The concept is as follows. We say that a process, that I mean a random process, is ergodic if its statistical averages are equal to or can be replaced with its time averages. That is, statistical averaging of any kind is equal to the corresponding time average of a given any sample function. Now, this is a very peculiar concept. It is a very useful concept, because without this concept you would not really practically be able to work with random processes, particularly when it comes to measurement of the properties of a random process. Let us look at very quickly the motivation for this property before I talk about the property itself. Motivation is as follows. As I said, our concept of a random process is, no matter how you look at it, basically it is a collection of infinite number of waveforms, and you do not know which waveform you are going to see. Suppose you suddenly perform the experiment, or you look at the random process as it occurs and display the waveform that you see, you will be picking up some arbitrary waveform which you cannot predict, right. Now, at a time, in typical situations, I will see just one such waveform from this infinite collection. So, if I want to practically measure its properties, average properties, let us say, if I want to measure the mean value, if I want to measure the autocorrelation function, right. Suppose I do not know a priori the density functions, how will I ever find out these quantities, right? Very difficult, because I have only one sample function available in front of me, right. I have just one sample function which I have observed. I do not know what are the other members of this infinite family. But on the other hand, this property, if it is valid for a given random process, helps me to find those properties just from a single sample function that you might have observed. So what you are saying is, even if I don't know, even if I can't average across the whole family because I don't have the whole family with me, if I just look at the average across the time of one sample function of the family, it's good enough. I get the same value, right? So processes which exhibit such properties are called ergodic processes. Fortunately for us, many physical processes which we work with are ergodic in nature, right? And therefore, many times we can obtain just the autocorrelation function by looking at the time domain autocorrelation function of a given sample function, or the mean value function by just looking at the mean value of a given time domain function, just like you do for any time domain, right? So for example, what is a time domain average? It will be simply this, right? Take the limit as t tends to infinity. That's a time domain average. This does not involve the density function of x. You are just taking the sample function, right, and integrating it in minus t to t. That's the sum of all the values that you see between minus t to t divided by the time interval. That's the time domain average. What is the corresponding statistical average? It will be x p x t x dx. That's the corresponding statistical average. So what you are saying is this is equal to this. Similarly for the autocorrelation function or any other kind of average, if this kind of relations hold for all time averages and corresponding statistical averages, the process is said to be strictly stationary, ergodic. Now, final statement in this connection. I know time. Just one final statement, because otherwise it gets discontinuous. If I denote by this space as a class of all stationary, class of all random processes, right? Class of white cell stationary processes. So this is all processes. The class of white cell stationary processes will be a subclass which satisfy those two conditions which I mentioned. The mean value function is independent of time. Autocorrelation function is dependent only on time difference. Strict sense stationary is a further subset of that, right? And ergodic is the smallest subset. Okay, that's just a statement I wanted to make and complete this discussion. Okay, so if a process is ergodic, it will also be strict sense stationary, it will also be white sense stationary, etc. Thank you.